Next, let's do a water pressure problem. It's number 32. It's about the Three Gorges Dam in China, which was built in 2008. It's the largest electrical generating capacity in the world from a dam. It's about 2,000 meters long and 180 meters high. So it's a long, skinny dam like this, about 2,000 meters that way, 2 kilometers long. That's more than a mile long, and 180 meters tall. That's pretty tall. That's almost as tall as 2 football fields stacked end to end upward. But it's not nearly as tall as it is long here. They tell you that it's made a reservoir bigger than Lake Superior in area. I should look that up. I'm sure doesn't look as big. It's probably like a really thick, long river that they're calling a lake. That's probably what it is, with a lot of ravines and stuff like that. 2 things to do in this problem. First is to estimate the water pressure at the base of the dam. We're assuming the water is at the top. That's the water level up there. What's the water pressure at the base? 180 meters down. And also, the second thing to do is to figure out the total force on the dam that comes from water pressure. And we're using SI units, yay! Though that does introduce an extra complication. We're given the mass density of water, not the weight density. We have to multiply by 9.8 meters per second squared to get the weight density, not in pounds, but in newtons per cubic meter. The pressure in general, pressure at depth H, they write down a real abstract equation at first as delta times G times H, where delta is the mass density, kilograms per cubic meter. G is the acceleration due to gravity, meters per second squared. And H is the depth in meters. This gives you a pressure ultimately in newtons per square meter is what it ends up being. It's not immediately obvious how that happens, but that's what this ends up being, is newtons per square meter. Delta for water is 1,000 kilograms per cubic meter. So imagine a cubic meter of water, a box this big. Its mass is 1,000 kilograms, corresponding to how many pounds? I'm not sure. 1,800 pounds, something like that. You can not lift it, okay? G is 9.8. So we end up with 9,800 H here. And if you are at a depth of 180 meters, replace H with 180 at H equals 180. And you're going to get the pressure in newtons per square meter. 9,800 times 180. 1,764,000 newtons per square meter. That's pretty high pressure, it sounds like. Yeah, if you were underwater at the base of this dam, under 180 meters of water, you would get crushed. Okay, you'd need some sort of wetsuit that protects you in some way pretty well. Pressure, physicists tell us, and I believe them, thinking about molecules, gets exerted in every direction. So this would be a pressure, you might call it a downward pressure on a thin plate, sheet of metal, sitting horizontally in the water at that depth, say slightly above the ground. It would also be the pressure upward on the bottom of that, even though it's based on the weight of the column of water above it. it gets still exerted in every direction. If you turn the plate sideways, it's pressure going sideways too. That's just the way pressure works. It's related to the fact that the molecules are essentially moving every direction. But the amount of pressure is still somehow based on the weight. Maybe the weight causes them to move faster. I'm not really remembering exactly how that works. That allows us to we can use that idea to figure out the total force on the side of the dam, the second part of the problem, in the following way. Figure out the approximate force on thin strips at approximately the same depth, and then add the results. Let delta H go to 0 to get an integral. If we're at depth H there, and the width of that is a small width, small height, delta H, what's the small amount of force on this really thin strip? I mean, it's 2,000 meters long, but maybe it's only a millimeter in height, okay? So you could still call it a relatively small area. If you wanted to go more extreme, you could do what, a micrometer or something in height. The small amount of area of that, delta A, would be base times height 2,000 times delta H. Pressure, again, is force per unit area. That's the area. The pressure is still, once again, this 9,800 H. Newtons per square meter times this many square meters. The small, well, okay, we got to use, I'm already dealing with the weight density of water there. So the small amount of pressure, delta P, on that thin strip should be the force per unit area at that depth H times the area. That's in newtons per square meter. This is in square meters. Oh, this is the small amount of force, sorry. The square meters would cancel, giving you newtons. But again, delta A is 2,000 times delta H, the area of the thin strip. 2,000 meters long, delta H meters high. $9,800 times 2,000 is, what's that? 19.6 million. 19,600,000 H delta H is the small amount of force on that thin strip in newtons. The total force on the side of the dam is the sum of the small forces. The approximation is right at the beginning here, because H is the thing that's approximately constant on the thin strip. This would all go right in there. Let delta H go to 0. The function we integrate is 19.6 million times H. Total force is going to be the integral of 19.6 million H dH. H is the depth from the top of the dam downward. At the top, H is 0. At the bottom, H is 180. So this is 0 to 180. Pretty easy integral to do. Though the numbers are big, you can switch to scientific notation if you want. 19.6 million would be 1.96 times 10 to the 7th. You could switch to scientific notation if you want. I'll type it in as I wrote it without scientific notation. It's going to be a big integral. Integral from 0 to 180, 19.6 million times h dh. What's that? Looks like 317,520,000,000 newtons. In scientific notation, that would be 3.1752. That's probably too many significant figures. Times 10 to the 11th, yes, newtons. Okay, if you wanted to know the entire force, it's an approximation. You know, we're making simplifying assumptions. Is that important to know for building the dam? Seems like it's more important to know the pressure, right? At the bottom, that would be of more concern as far as like the dam cracking. Was there a question? The 1,000 was the mass density of water, 1,000 kilograms per cubic meter. Multiplied by 9.8 to get the weight density in newtons per cubic meter.